Okay, so last time we have discussed about the moment transfer. This time we will complete the bielliptic transfer. And bielliptic transfer, as I stated earlier, is nothing but combination of two moment transfer. And let us go and work out the corresponding problem. So, we have one initial orbit here, and this is the final orbit. Initially, the satellite is located at A, this is the center of attraction. Then to get into this orbit, sometimes if you look energy wise, so another kind of manipulation may be better, and this we represent as. So, this is your transfer orbit. We write here semi major of axis of this as A. Let us write this as A 1 or A T 1 transfer orbit. Then to get into this orbit, we apply another impulse. So, this is also the moment transfer. Moment transfer, and this is also moment transfer. So, first impulse is applied at A, the next impulse will be applied at B, and the last impulse will be applied at C. So, here this is delta V A, delta V B, and here in this point delta V C. Direction is not fixed. Okay. Delta V C in the opposite direction, okay, but we show it like this. So, working principle is the same as we have done for the moment transfer, nothing different. Okay. So, delta V A. So, I write in short because already I have worked out all the details. So, here in short I will write 2 mu by, and initial radius is obviously this is r I and this radius is r f. Why the name is bielliptic? Because you have the first ellipse half of that and the second ellipse half of that. Okay. So, 2 by mu r I minus 1 by A T 1 minus mu by r I. This is the velocity in the circular orbit, this is velocity in the elliptical orbit at A. So, this is the impulse required, and from here mu by r I we take it as common. So, this gets reduced to 2 by 2 minus 1 by A T 1 under root minus 1. We have written as V I C. So, we will follow that notation V I C, or let us write as V A C to make it more convenient rather than writing R I. This is A, and here V notation will be using a small a, b and c. So, V A C velocity at A in the circular orbit, or V A C equal to nothing but your V I C, or maybe let us forget this V I C, write this as the V I C. This times 2 minus 1 by a t 1. So, what is the semi major axis of the this orbit? So, this will depend on the r I and this r b. So, this we can write as 2 minus 1 by r I plus r b divided by 2, this whole under root minus 1. Okay, r I we have taken outside. So, we should also put here r I here in this place. So, this part is missing, r I and here 2 r I. So, 2 r I means we get here 2 r b divided by 2 r b, 2 r I cancels out. So, 2 r b divided by r I plus r b under root minus 1 . 2 times n star divided by 1 plus n star under root minus 1. What we have done here? So, we have 2 r b by r I plus r b is there. So, we have divided numerator and denominator by r I. So, r b by r I and this gets 1 plus r b by r I. So, we get here 2 n star 1 plus n star, where n star we have written as r b by r I. So, here we can name this as equation 1 V I C 2 n star divided by 1 plus n star minus 1. Now, the impulse required at B. So, this is very easy part, only thing the concept you have to understand, it is not more than 12 class mathematics. But the in actual practice, once you apply it, there the you are considering transfer from one planet to another planet. So, the case gets complex because of the presence of the planet, the sphere of influence is there. So, you are not taking just such a point. So, first we will do one problem using just a point mass of considering one asteroid which is massive asteroid, but it is just like a point. So, that the problem gets easy to work out. And there we neglect the sphere of influence, okay, and based on that then we work. So, I will come to all those points. So, due course of if I solve some problems, we will get to know all the concepts. So, impulse required at B, this will be equal to, so delta V B. So, velocity at point B in the second elliptic orbit 1 by mu times 1 by C p. Here we are giving this impulse. So, delta V b we are looking for. So, what is the velocity initially at this point and what is the velocity finally at this point. So, this orbit is different, this is a t 2, it is a semi major axis. So, this is the semi major axis of first transfer orbit of first transfer orbit. and this is semi major axis of the second transfer orbit. So, we use the same equation as we have done here, used here this part, to mu by r I gets replaced by r b. Okay. So, after providing the impulse, this is going in the second orbit. So, A now it has been thrown into the second orbit A T 2 and minus to mu by r b, the radius has not changed. Before impulse, this is related to A T 1. And then we need to simplify it. A T 1 we know this quantity is r I plus r b divided by 2 and A T 2 is r b plus r f divided by 2, as it is evident from this figure. This is your r b from here to here and this is r f. So, half of that, this constitutes semi major axis of this orbit. Okay. Similarly, we have to calculate for this orbit. So, we can use these two quantities here and insert here in this place. So, this we get as mu, we can take it outside and this becomes 2 divided by r b minus 1 A T 2 is r b plus r f divided by 2. So, 2 comes in the numerator. Mu times. Now, here the way this is appearing. So, what we do, see r I is in nowhere the r I is manifest. So, so accordingly we have to divide it and write it in a proper way. Okay. So, N star is the quantity we have defined as r b by r I. Okay, and the quantity n we have defined as r f by r I. These are the only two distances which we are concerned with. This from here to here, this is your r b, from this place to this place. And this distance from here to here, this turns out to be r f, and the distance from here to here, this is your r I. Okay, so, we need to rewrite this little bit, so that it gets into a proper format. So, first we will write here in this place, try to accommodate here. Okay, we divide the numerator and denominator by r I. So, this is 2 r f by r I and r b by r I, this gets, and here R B plus R F is there. So, we have to do it in a proper way. So, what we will do, that we will write here R I and R B by R I plus R F by R I in this under root minus R I is present here. So, we can rewrite this as 2 divided by R B by R I Okay, so, this gets reduced in the form 2 R F by R I, this is R F. So, 2 n divided by R B by R I is n star, okay. And then R B by R I here, this becomes n plus n star, R F by R I is R B by R I is n star and the R F by R I is n. So, I should reverse it. So, this is n star plus n. Okay, and the R I is also there, R I, and then minus, and this square root is also present, then a square root 2 divided by R B by R I is n. N star, okay. Then R I and times 1 plus n star. And here once we have taken this mu under root. So, mu is going without under root sign I have written. So, this is the correction here. So, mu under root, once we take it outside R I. So, this is mu by R I under root and then 2 n divided by n star times n star plus n under root minus 2 divided by n star 1 plus n. More compactly, this can be written as delta V B equal to mu by R I is now nothing but V I C, and if we take 2 by n star outside, so this gets reduced to n divided by n star plus n under root minus 1 by 1 plus n star under root. So, this is equation 1 we have written in terms of V I C, this is we have written in terms of V I C again, this is equation 2. Now, you will see the advantage of writing in this way once you solve the problems. So, your effort in the calculation, this gets reduced. Okay. Even if you have to do computer programming, so there also it is a very convenient. Okay. So, this is delta V, and this should not be understood as the point C. This is circular orbit, standing for circular orbit. Okay. The last point is the C. At C, once the satellite reaches here in this orbit by coasting throughout from this place to this place. So, at this point impulse is required. So, impulse here energy is higher in which one? You will see that as we have written the energy E prime equal to minus mu by 2 a. So, the semi major axis for the this pink orbit, the AT2, okay, this is larger than RF, okay, and therefore, energy in this orbit will be more, as it is evident from this place, minus mu by 2 a. Okay, we go on the next page and then we explore this. See, E equal to minus mu by 2 a once we are writing. Okay. So, if it is circular orbit, so A gets replaced by R. So, in that case this is mu by 2 R E prime. So, at the point C, this is the energy in the orbit, while and this we can write as R C, or we have written as the R F. Okay. So, E prime R F in the circular orbit, and E prime at C in the elliptic orbit, this is C C we can write here, circular orbit, and this is in the elliptic orbit. So, this is minus mu by 2 R F plus R B. So, R B, if it is much larger than R F, so you can see that, or say R B is greater than R F. So, you can calculate what will be the energy. This is valid for both the elliptic and the circular orbit. Why? Because I prime equal to V square by 2, E prime equal to V square by 2 minus mu by R, and V in the circular orbit is mu by R under root. So, this gets mu by R minus mu by R, and once you subtract it, so immediately you can check that this quantity will be mu by R can be taken common, 1 by 2 minus 1. So, this is minus mu by 2 R. So, this is in the circular orbit. So, this result is valid for both the circular orbit and the elliptic orbit, provided you properly insert the value for the V. So, here in the circular orbit this is the energy, and the elliptic orbit this is the energy. So, that means you need to reduce the velocity at this point. So, velocity, the actual velocity after coming from this place to this place, that will be in the elliptical orbit V E at C, V in the elliptic orbit at C, or V E F, whatever we want to write. Okay. And then one impulse needs to be applied here in this direction. I have shown here in this direction, which is customary to show it like this, but this will be the opposite one. Okay. So, you have to basically apply impulse here in this direction, delta V C, so that the velocity is reduced and this orbit is circularized. Okay. So, following this notation, whatever we have done earlier, so same notation we can work for the impulse required at C. So, delta V C, the impulse required so final velocity in the at point C in the elliptic orbit. So, mu 2 mu by R. Okay, for this we need to R F, we have used here notation at this point. So, from here to here, let us see, this point to this point, this distance we have to take. Okay. So, 2 mu by R F minus mu by A T 2. Okay. This under root, this is the velocity at point C in the transfer orbit minus velocity in the circular orbit at point 2, and that will be mu by R F. A T 2 is nothing but R F plus R B divided by 2. So, this goes in the numerator or mu 1 under root we take here, and this is 2 r f plus 2 r b minus 2 r f divided by we divide numerator and denominator by r I. This gets reduced to 2 r b by r I, r f by r I, and then multiply here by r I, and similarly write here r f by r I plus r b by r I under root minus 1 by 2 r b by r I we have written as n star, and r f by r I as n. And r I we can take it outside from both the places. And if we take under root n here from this place, this gets reduced to 2 n star n plus n star under root minus 1, and this is nothing but your quantity V f in circular orbit. This circular orbit, the C v notation we have used, this I wanted to avoid, because V a V I C. Rather than using or properly tag it. VFC I will write here, so that you do not get confused. So, this is VFC 2 n star n plus n star under root minus 1. VIC is the velocity at A in the circular orbit. This is very important to note, because the notation I have used, these two have got mixed up. Velocity at A in the circular orbit, and VFC is the velocity at C in the circular orbit. So, this C stands for circular orbit. this stands for circular orbit. So, we do not have to confuse this. Or either just indicating V I and a V f, and we can delete the C. This is the only way we can do. So, this C either I drop everywhere, then we do not confuse with this point C, or either I rename this point C. These are the two options of doing this. So, A, B, C, let us okay, I am leaving it as it is, V I C indicating by clarification given by these two statements. Okay. Maybe in your once you note it, so at that time you can make it D instead of C. So, that we do not confuse with the circular orbit C and the point C. Okay. Now, we have got one more thing we have to check here. We have subtracted from here in this place, this is the velocity in the elliptic orbit, and this is velocity in the circular orbit, which is the final orbit. We have not subtracted from the final orbit velocity the elliptic orbit velocity, and we need to check that indeed this quantity turns out to be positive. This is important to check, otherwise you have to take the magnitude of this quantity. So, delta V c equal to V f c and then 2 n star divided by n plus n star. Minus 1. We rewrite it in this way. So, what we can see from this place, n by n star is less than 1, okay, and therefore, the denominator will be less than 2. So, n by n star plus 1, this will be less than 2, and therefore, this quantity will be greater than 1. So, this quantity is greater than 1, and from there if you subtract 1. So, this quantity delta V c turns out to be greater than 0. And now, you can add all of them, delta V equal to delta V a plus delta V b plus delta V c. So, this is the impulse, total impulse required. Limiting case. Limiting case, n star, which is reflecting the intermediate orbit, tends to infinity. If that happens, then your delta V c, this gets reduced to, we can check from this place, this under root 2 minus 1 times V I c divided by root n. Okay. Similarly, delta V b will get reduced to delta V b, we have worked out here. Here this is as n star tends to infinity. So, you can see that this quantity will tend to 0, this quantity will become 0. Other quantities accordingly we can write here. This is in the denominator n star. So, simply this will tend to 0, this also goes to 0. So, we get here delta V equal to 0, delta V B, this quantity will be 0 and delta V A. Delta V A we have calculated here. If n star tends to 0, so in that case this is delta V A. We put n divide by n star in the numerator denominator. So, this gets reduced to 2 1 divided by n star plus 1 under root minus 1 times V I C. So, n star tends to infinity, this gets reduced to 2 minus root 2 minus 1. So, this is root 2 minus 1 times V I C. Therefore, total impulse required delta V C equal to root 2 minus 1 V F C plus root 2 minus 1 times V I C or either both of them writing in the same V I C, then in that case this will appear as 1 plus 1 by 1 plus 1 by root n times V I C, total delta V total. Okay, so, this conclusion what we have drawn here, this is important. What we can see that at delta at B we do not require any impulse. Okay. At C we require impulse and at A we require impulse. Why? Because this is very evident that your E prime this equal to minus mu by 2 A as A tends to infinity. So, E prime this becomes equal to 0. Okay. A tends to infinity, this quantity is 0. So, approaching from the orbit at B, okay, and then again starting from this place. So, here the total energy is 0. And therefore, starting also and approaching also both the energies are 0. So, there is no change in the velocity, okay, because the position is not changing here. Okay. If position is not changing means potential energy is not changing, which in this case here mu by r this equal to also 0 with minus sign here. So, there is no change in velocity here and therefore, at B we do not require any impulse and this is what is we obtained from this equation. So, at delta at A and B only thing that we need to give the impulse. Okay, so, using this technique, if you have to send the object in the parabolic orbit, you can work it out. The satellite you have to send in the parabolic orbit or either multiple orbits, different kinds of orbits can also be mixed up. And what is the simplicity? That you have to use this equation V a square or V equal to mu times 2 by r minus 1 by A. Which we have earlier derived as this Viva integral. Okay, so, by this we have finished the bielliptic transfer. Now, it comes to whether the bielliptic transfer is beneficial or the Hohmann transfer is beneficial, which one should be used. So, it is a very simple here to see that in the bielliptic transfer, because it is going in a larger orbit. So, the amount of travel, the time to travel from A to B from this point to this point and then again from B to C, it will be much larger if we directly go from the inner orbit to say from this place. From here if I directly go to this point, so this time will be much smaller, okay. Immediately I can achieve in this, and if I have to come to this, so only this half of this time extra is required. So, you require here the extra time to travel to this point and again extra time to travel along this one. Okay. So, in the bi-elliptic transfer it may be better than the Hohmann transfer in terms of energy consumed, okay. And it depends on the condition which we need to look into. Okay. But the time of travel it drastically increases, and therefore, this kind of orbit can be used if and only if you are not worried about the time. If you are worried about the time where the time is mandatory to be maintained, okay. So, at that time we have to resort to the Hohmann transfer, or either even if you require the faster in least time you have to do. So, you have to go for some other orbit. Okay. The shortest will be a straight line going from one point to another point with infinite velocity, but this is not practical, you cannot get infinite velocity, okay. And therefore, the shortest possible time you get always in the hyperbolic orbit, okay. Next it goes in the parabolic orbit and then the elliptic orbit. So, accordingly we choose our orbit, and it will also depend on the automatically you will be forced to use that kind of configuration. Say here in this case, as we were discussing earlier, that if one satellite is at A, okay, another satellite is at B, and you have to catch satellite A, okay. You have to catch satellite B, means you have to dock satellite A with B, and that is to be done at point C. Okay. So, in that case you have to send it in a faster orbit. So, mostly once you calculate this faster orbit, it will turn out to be a hyperbolic orbit. Okay. This we need to work out. Okay. So, I will do this problem also related to this, it will come in the rendezvous problem. So, one change I am going to do, that the 12th week lecture I will shift to the 11th week. This is the 10th week we are running with, okay. And 11th week lecture I will shift to the 12th week, so that some continuity is maintained. I have got the feedback that the lectures are becoming very lengthy, and we do not have enough time to study. Okay. In 1 week, sometimes for perhaps for 3rd or 4th week, the 7.5 hours has been covered instead of 2.5 hours what should have been. Okay. So, students are not able to give that much of time, but getting into the concepts, okay. Once I need to explain all these things. So, that takes time, okay. Writing few equations, or just I bring the slides and present the equations. So, it can be very fast, okay. I can finish in short time, but if I try the concepts properly and once I write it. So, the concepts get developed properly. If I do not write one by one, so you will not know from where what is coming, as usually is done in the book. Few equations are given and then the chapter is closed. So, I have derived all the equations sequentially, and it is required for your proper understanding, and even if you want to use for professional purpose, all these things can be used. So, we close this lecture here and we will continue in the next lecture. Thank you very much.